Hey guys, this is Harold L.R. Watkins back with another video. And today I am demonstrating AutoSec UDS Conformance Workbench. This tool is designed for automotive embedded software verification and validation. The goal is to help review UDS diagnostic behavior by comparing real diagnostic traces against an expected ECU diagnostic specification. The important part is that this is not just a hexacoder. A decoder tells you what a service means. The workbench goes further by asking whether the ECU response matches the requirement, whether the service was allowed in that diagnostic session, whether security access was satisfied, and whether the test procedure followed the expected flow. AutoSec UDS Conformance Workbench is built around a simple verification and validation workflow. Load a diagnostic specification, load a trace, run validation, review findings, and export a triage report. The diagnostic spec acts like a lightweight version of the type of expectation and validation engineer would normally receive from a requirement source, CDD or ODX, or another diagnostic design artifact. The trace represents what actually happened during testing. The value of the tool is in comparing expected behavior against observed behavior. The workbench layout, you will see on the left side, I have the trace table. This shows each diagnostic step, the request, the response, the declared session, the declared security state. On the right side, you will see the decoded detail panel explains the selected request and response in plain language. At the bottom, you will see the findings table which shows the validation results. This is where the tool reports pass, fail, blocked, or info findings. This layout is designed so a tester can quickly move from trace evidence to decoded meaning to validation judgment. Okay, so I'm going to load the spec first. Let's see here. Then I'm going to load a pass trace, and I'm going to run the validation. So now that I loaded the APIM diagnostic specification, APIM is the infotainment module. So this example aligned with infotainment software integration and diagnostic validation. The spec defines supported services, supported DIDs, allowed diagnostic sessions, and security access requirements. This keeps the rules outside the GUI and makes the tool more flexible. If I wanted to validate another ECU later, I can create another spec instead of rewriting the application. As for when it comes down to running validation, the tool evaluates each diagnostic step against the APIM spec. This trace includes a diagnostic session control request. As you can see, we have the control request, read data by identifier request, mission service 22. One important point is that a pass does not always mean the ECU returned positive. Doesn't always mean that the ECU returned positive responses for everything. In validation, a correct rejection can always be could also be a pass. For example, if a DID is out of spec and the ECU rejects it with MRC 31, request out of range, that is a correct behavior. That is the difference between a decoder and a conformance checker. The workbench understands that some negative responses are expected and correct. So here I can select a read data by identifier request. Service 22 is used when a tester requests ECU data using a DID or a data identifier. A positive response to 22 is 62. So if the request is 22F8C and the ECU responds with 62F1 8C followed by the data bytes, the workbench recognizes that as a positive DID read. It also checks whether the DID is actually allowed by the spec. The second part is important. A positive response is not actually good if the DID is undocumented or outside the allowed diagnostic design. So here you will see it starts the session. So the tool requests to start a session, and then the ECU or the APIM responds with a positive response. Then the ECU performs a service request, read data by identifier, and the APIM responds with a positive response. Same here, letting the ECU know that the tester is present, and positive response from the ECU or APIM. So with that, I'm going to open up a field trace. And run validation. Okay, in this example, we are using a field trace because it shows how the workbench separates ECU behavior from test procedure behavior. The trace begins with a diagnostic session, which you can see here, and a security access C request. The C request succeeds, then the send key step fills with NRC35 invalid key. Because the security unlock did not complete, the security state remains locked. After that, the trace attempts a write data by identifier request using service 2E. The ECU rejects it with NRC33, security access denied. That rejection is the correct ECU behavior, but the overall test still fails because the test proceed procedure or still attempted a security gated service while security was still locked. So in other words, it's to run through it. Here, the tool starts a session. We have a positive response. The tool requests the seed here. Request for seed, you can see here. The ECU responds positively, says here's the seed. The tool calculates the seed using its algorithm and sends back a key. You can see here, sends key, and then the ECU responds invalid key. Hey, you sent the wrong key. So the module is still locked. However, even though it's locked, when you come here, the tool still attempts to write to the DID, even though the module is locked, and you can see that here. So write data by identifier and negative response. So the module responded correctly by saying security denied 33, but the tool shouldn't have attempted to write to the module. And then you come down here, and this will explain the findings. This is where the tool becomes useful for verification and validation. The workbench does not just say red equals bad, it explains why the finding failed and what the likely next step should be. For the 27 security access failure, the actual response is 7F2735. That means the ECU rejected the key as invalid. A likely cause could be a seed and key mismatch, wrong security algorithm, wrong key data, or a test tool issue. For the 2E write data by identifier step, the workbench reports that the request was made while security was locked. The ECU returned 7F to E33, which means security access denied. In this case, the ECU may be conforming, but the test procedure cannot pass as written. So when I come here to export it for, this will be the same. So I have to keep it on 3. It'll be the same. So now I exported the triage report. The report captures the module, trace name, spec version, overall verdict, summary count, individual findings, expected behavior, actual behavior, possible cause, and recommended next steps. This is useful because validation work is not only about finding a failure, it is also about communicating the failure clearly enough that software, diagnostic systems, or supplier teams can act on it. The architecture is intentionally separated. The GUI is only the presentation layer. The diagnostic logic lives in separate modules for decoding, spec loading, rules evaluation, and report writing. That matters because the same validation engine can later support a command line workflow, automated regression tests, CI pipelines, or continue integration pipelines, or failure integration, future integration with trace capture tools. A workbench like this should not trap the logic inside button click handlers. And returning to the app, get this out of the way. The industry value is in lightweight, repeatable diagnostic conformance checking. A validation engineer often needs to answer questions like, was this service allowed in this session? Was security access unlocked? Was the did defined in the spec? Did the ECU reject the request correctly? And did the test procedure follow the expected sequence? AutoSec UDS Conformance Workbench is an early version of a tool built around those questions. It helps turn raw diagnostic traffic into evidence, verdicts, and triage notes. To summarize, AutoSec UDS Conformance Workbench validates UDS traces against a machine-readable diagnostic spec. It decodes services and responses, tracks sessions and security behavior, and identifies performance issues, separates ECU failures from procedure failures, and exports V&V-style reports, which is validation and verification style reports. The next roadmap items would be ISO TP reassembly, live cam capture, DOIP support, seed and key analysis, ODX or CDD import, PDF reporting, and cybersecurity mapping. Thank you for watching this demonstration of AutoSec UDS Conformance Workbench.